Hello everyone. So welcome to our lecture number 18. So in lecture number 18 we will discuss about your applications of Gauss theorem. So let's start our topic, applications of Gauss theorem. So before entering into this concept, let's first discuss different shapes of Gaussian surface. Different shapes of Gaussian surface. Suppose for point charge. For point charge, always remember this is suppose your point charge Q, and the nature of Gaussian surfaces are concentric spheres. Concentric spherical Gaussian surface. So these are the Gaussian surface. So different steps means here you have to write concentric spherical Gaussian surface. Okay. Next, for infinite linear charge. Infinite linear charge. So this is your infinite linear charge. To extend up to infinite. So for this, the nature of Gaussian surface is coaxial cylinder. So here we can say coaxial cylindrical Gaussian surface. So the answer is coaxial cylindrical Gaussian surface. Okay. Next, for infinite sheet. For infinite sheet. So this is your infinite sheet, suppose. Infinite charge sheet. So if you will observe this from one side, it behaves like this. From one side, if you will observe the infinite sheet, then it behaves like this, linear in nature. And the nature of Gaussian surface, here we can assume it is just like pill box. So for different cases, you have to draw the Gaussian surface as shown in the figure. This is pill box. This is the Gaussian surface. I hope it is clear. Yes. So next come to our first application, that is electric field due to charged thin wire of infinite length. So let's give heading electric field due to charged thin wire of infinite length. Yes. Suppose this is your charged thin wire of infinite length. I am going to draw the diagram. And the nature of Gaussian surface we have just discussed, that is your cylindrical in nature, coaxial cylinder. Here we can assume that this pink color portion is our Gaussian surface, coaxial cylindrical Gaussian surface. And let the length of this cylinder, that is your L, and the charge enclosed within the cylindrical Gaussian surface, that is your Q. And here we can mention L is the length of the coaxial cylindrical Gaussian surface. Yes. And whose radius is smaller. Yes. So mention this thing, L is the L and R, that is the length and radius of coaxial cylindrical Gaussian surface. Yes, and what is Q? Let lambda is the linear charge density. Lambda is linear charge density and Q is the charge enclosed. Q is our charge enclosed. So we can mention lambda is equals to Q by L, which implies Q is equals to Q enclosed is lambda into L. Here we can write like this. Yes. So what is our M? Our M is to find electric field at point P. This is suppose point P. Yes. Okay. So our aim to find electric field at point P Yes. So in this case, what we have to do now, observe this thing. There are three ocean surfaces. Sorry, there are three surfaces. One is your top surface, then second one is bottom surface, another thing is bottom surface. Bottom is your this one, white color portion, and third one is your curved surface. So in each case we can write the area vector. So in case of a curved surface, let this is your first surface, then this is second one, top surface is second surface, and bottom surface is third surface. For first surface, what is your area vector? This is our dA1 vector. This is your dA1. And for second surface, this is your area vector dA2. And for third surface, area vector is outer normal, that is dA3. And in each case, for the dA1 surface, what is your electric field intensity direction? Direction of electric field intensity is outward, radially outward. And for top surface, direction of electric field also along positive x-axis, that is your electric field direction. And for third surface, bottom surface, this is the direction of electric field. Yes, I hope the diagram is clear to all of you. Okay. So as per Gauss theorem, what we can write? As per Gauss theorem, we can write, we know total flux phi is equals to Q by epsilon naught, and instead of phi we can write closed integral E vector dot ds vector or E vector dot dA vector equal to Q enclosed by epsilon naught. Enclosed charge is Q. Yes, this closed integral can be written in this way, that is integration E vector dot dA1 vector, this is for surface S1, plus integration E vector dot dA2 vector for surface S2, plus integration E vector dot dA3 vector surface S3 is equals to Q divided by epsilon naught. Okay, so for surface S1, that means your curved surface, the angle between E vector and dA1 vector, the angle is 0 degree, both are parallel. So we can write integration E dA1 cos 0, for surface S1. Then for surface S2, angle between E and dA2, E vector and dA2 vector, that is your 90 degree. So we can write E dA2 cos 90 plus integration S3 E dA3 cos 90 is equals to Q divided by epsilon naught. And cos 90 is 0, the whole integration result will be 0. So next thing is, we can write E is constant, cos 0 is 1, then integration S1 dA1 is equals to Q divided by epsilon naught. So integration dA1, okay. So if you will integrate all such small areas, you will get the curved surface area, whose value will be 2 pi r into L. Because radius is r, the curved surface area will be 2 pi r into L. So E into 2 pi r into L is equals to Q divided by epsilon naught. I hope it is clear, which implies E is equals to Q divided by 2 pi epsilon naught r into L. Q divided by 2 pi epsilon naught r into L. And we know Q by L is charge per unit length, that is your lambda. We know charge per unit length, charge divided by length, that is your lambda. Charge divided by length is lambda. Q by L is lambda. So instead of this we can write lambda divided by 2 pi epsilon naught into r. Lambda divided by 2 pi epsilon naught into r. Yes, so this is one answer. Also we can write it as E is equals to, if we will multiply 2 on both numerator and denominator, then it will be 2 lambda divided by 4 pi epsilon naught into r. That means 2k lambda divided by r. What is small k? Small k is 1 by 4 pi epsilon naught. So clearly we came to know, from this expression we came to know that E is proportional to 1 by r. Clearly we came to know E is proportional to 1 by r. So from the expression we can mention, thus from expression we know E is proportional to 1 by r. So the graph versus E versus r, the graph between E versus r will be, if we will draw the graph, then it will be like this. E along y axis and r along x axis, and E versus r. This will be rectangular hyperbola. Yes, this will be rectangular hyperbola. Yes. So if it is asking to draw the graph between log E versus log r, what we have to do? So give heading graph between log E versus log r. Graph between log E versus log r. So we know E is equals to 2k lambda divided by r, and 2k lambda is constant quantity. Take it as a. Take it as a. That is a by r, where a is a constant whose value is 2k lambda. Whose value is 2k lambda. So by taking log on both sides, log E is equals to log into a by r, and log a by r can be written as log a minus log r. It can be written log a minus log r. So it will be log E is equals to minus log r. We can write minus log r plus log a. And if you can compare this thing with y is equal to mx plus c, then it will be y is equals to m into x plus c. So from this we came to know, from this we can predict, along y axis we have to take log e, along x axis we have to take log r. In this situation the slope will be minus 1, negative, and c is the intercept whose value is log a. Whose value is log a. So how to draw the graph? The graph will be like this. Log E versus log R is a straight line whose slope is negative. Straight line having slope negative. So log E versus log R graph. The graph is like this. Okay, this is your result. So this is about your electric field due to charged thin wire of infinite length. So this is our application 1. Next come to second application. Next come to our second application, that is to find electric field due to thin charged spherical shell. So electric field due to thin charged spherical shell. Yes. So let this is your spherical shell. This is our spherical shell having radius capital R and charge present on its surface is, let it be Q. This is the center O and this is our radius capital R. Yes. So let sigma is the surface charge density. Sigma is surface charge density. So sigma is equals to charge and charge distributed is Q. Charge by area, Q divided by the surface area will be 4 pi r square. So 4 pi capital R square. This is the value of sigma. So which implies Q value is equals to sigma into 4 pi r square. The value of Q will be sigma into 4 pi r square. So next we have to find electric field intensity for case 1. Case 1 inside of spherical shell. Case 1 is inside of spherical shell. Inside of spherical shell, what will be the value? Now see this thing. So to find the electric field inside the spherical shell, let's think about the Gaussian surface. Yes. So at a distance smaller, let us consider a Gaussian surface. It is a sphere having a radius smaller. This is your Gaussian sphere. And within the Gaussian sphere, the charge enclosed is 0. Inside the Gaussian sphere, किसी भी charge नहीं. So inside the Gaussian sphere, 0 charge is enclosed. So we know that means here inside of spherical shell means small r is less than capital R. So we know flux phi is equals to Q divided by epsilon naught. Q enclosed by epsilon naught. Phi means closed integral E vector dot dA vector. That is your Q enclosed divided by epsilon naught. So here Q enclosed is 0, which implies we can write E is equals to 0. We can write this thing as 0 by epsilon naught. So E is equals to 0. So always remember E inside is 0 in case of spherical shell. E inside is 0. Next come to our outside of spherical shell. Outside of spherical shell, that is case 2. Case 2, that is outside of spherical shell. Let's solve this case in right hand side. Case 2. Outside of spherical shell. That means let this is our spherical shell. Outside of spherical shell means at a distance smaller. Let us consider your Gaussian sphere. So this white color part is our Gaussian sphere. This is our Gaussian sphere. For outside case, small r is greater than capital R. For outside case, small r is greater than capital R. So in this case, inside the Gaussian sphere, total charge is enclosed. Again, we have to write phi is equals to Q in divided by epsilon naught, and phi is equals to closed integral E vector dot dA vector, that is equals to Q divided by epsilon naught. Because now see this thing, if you will observe this one, this is your dA vector, this is your area dA, and whose area vector is outer normal dA vector, and whose electric field value in outward direction. Yes, so E and dA both are in same direction, so we can write closed integral E dA cos 0, that is Q divided by epsilon naught. Because inside the Gaussian sphere total charge is enclosed. Inside of Gaussian sphere, the total charge is enclosed within the Gaussian sphere. Within this red color Gaussian sphere, the whole charge Q is enclosed. So we can write Q enclosed within the Gaussian sphere is total charge Q. Yes, so cos 0 is 1, take E at outside, then closed integral dA equal to Q by epsilon naught. So if you will add all such dA elementary area, then you will get the surface area of this Gaussian sphere. So integration dA means, always remember, it is the surface area of Gaussian sphere. So E into surface area of Gaussian sphere will be 4 pi small r square. because its radius is smaller, that is q by epsilon naught. So E value will be q divided by 4 pi epsilon naught into r square. This is your E out, or we may write k q by r square. 1 by 4 pi epsilon naught is k, so k q by r square. This is the value of E out. So clearly we came to know, thus E is proportional to 1 by r square. E out, you may mention E out is proportional to 1 by r square. This is the case. So for this case, case 3, at surface of spherical shell. This is very simple case. Case 3. Case 3, at surface of spherical shell. At surface of spherical shell, all of you remember, small r is equals to capital R. At surface, if you will consider a point and if you will draw the Gaussian sphere, then that radius of Gaussian sphere is equal to radius of the spherical shell. So small r is equal to capital R. So E on surface will be equals to, simply E out is equal to how much? Q by 4 pi epsilon naught small r square. So this will be Q by 4 pi epsilon naught into capital R square, or you may write K into capital Q by capital R square. So it is a constant quantity. So E on surface is constant quantity. If you will draw the graph, so what will be the graph? Now see, nature of the graph will be, so this is your E versus smaller, E versus smaller. So smaller can be taken in positive x direction or negative x direction. Yes. So E inside is 0. E inside is 0. So generally, let's draw this cell diagram. This is suppose that cell. Okay. Let's think this is your spherical cell. This is that spherical cell. Let us think. So you can think that this point is your capital R point. That is, this represents your surface. This is your capital R. Yes. So, and this is your center. The center is 0. 0 is your center. So in this case, how to draw the diagram? How to draw the graph? E inside is 0. E inside is 0 means 0 to capital R, the intensity value is 0. 0 to capital R, the intensity value is 0. So you have to draw the line like this. 0 to capital R, intensity value is 0. In both x direction and negative x and positive x, you may draw the graph. On surface, it is maximum. Let it is maximum on surface. This is the graph. It is maximum on surface. Then E outside is proportional to 1 by r square. Then it decreases. This will be the graph. Yes. So this is the nature of this graph. This is the nature of the graph. So from this, you can mention this representing E in is equal to 0. E in is equal to 0. This represents E on surface, and it is your E out proportional to 1 by r square. In left side also, E out proportional to 1 by r square. So this is the nature of this graph, E versus r graph. I hope it is clear. This is about your electric field due to thin charged spherical shell. Next comes to application number 3, electric field due to non-conducting solid sphere. So next we will discuss electric field due to non-conducting solid sphere. Application 3. Electric field due to non-conducting solid sphere. Yes. So in case of non-conducting solid sphere, the charge is distributed throughout its volume. The charge is completely distributed throughout its volume. Keep it in mind. So here charge is distributed throughout the volume like this. So here we have to consider volume charge density, and the radius is, the center is O, the radius is your capital R. Capital R is the radius. Yes, so let us consider, let rho is volume charge density. Rho is your volume charge density. So rho is equals to total charge distributed is Q. So Q divided by charge per volume. Volume will be 4 by 3 pi capital R Q. So Q enclosed value will be Q enclosed, Q is equals to rho into 4 by 3 pi capital R Q. This is the value of charge, total value of charge. Next we have to follow, for case 1 we have to find electric field due to non-conducting solid sphere inside of sphere. So let us consider case 1. Case 1 is for inside of sphere. This is not hollow, this is solid. So inside of sphere means small r is less than capital R, we have to consider. Yes, so inside of sphere, first draw the diagram. Yes, let these are the charges, and we have to think Gaussian sphere. So let at a distance small r, let us think a Gaussian sphere. This yellow color part represents your Gaussian sphere, and we have to find the value of electric field at a distance smaller. At a distance smaller, let point P is there. At a distance smaller, let point P is there. So we know phi is equals to Q in divided by epsilon naught, and we can write instead of phi integration E vector dot dA vector is equal to Q enclosed divided by epsilon naught. So here our first duty is to calculate enclosed charge within the Gaussian sphere. So here Gaussian sphere is yellow color sphere is Gaussian sphere, and the enclosed charge value will be red color portion. In the red color portion, the amount of charge available will be your Q enclosed. So what will be the value? So remember how to calculate. Within the whole volume, the total charge enclosed is Q. The whole volume is 4 by 3 pi capital R Q. So here I am going to mention, this is your volume, this is your charge. Yes, so in volume 4 by 3 pi capital R Q, amount of charge enclosed is Q. In unit volume, the amount of charge available will be Q divided by 4 by 3 pi capital R Q. So for the red color portion, the volume will be 4 by 3 pi small r Q. So for unitary method, 4 by 3 pi small r Q volume. Within the volume 4 by 3 pi small r Q, the charge enclosed will be Q divided by 4 by 3 pi capital R Q into 4 by 3 pi small r Q. So after solving, you will get 4 by 3 pi cancelled out. Then it will be Q into small r Q by capital R Q. This is your Q enclosed. This is equals to Q enclosed, small r Q by capital R Q. Yes, and as per the previous process, we can write E dA cos 0. If we will consider a small elementary area, then this will be the dA area vector, dA vector, and your electric field will be E vector. Both are in same direction. So E dA cos 0. So closed surface integral E dA cos 0, that is equal to Q enclosed by epsilon naught. Q enclosed is Q into small r Q by capital R Q into epsilon divided by epsilon naught. So cos 0 is 1. Then take E at outside. Then integration closed integral dA is equals to small r Q by epsilon naught into capital R Q. So what is integration dA? So remember, integration closed integral dA means it is the surface area of Gaussian sphere. So that is 4 pi r square. So E is equal E into 4 pi r square. E into 4 pi small r square is equals to Q r Q divided by epsilon naught capital R Q. Then after solving, r square cancel हो गया, तो remaining small r is there. So E is equals to, we can write the value of E will be equals to Q divided by 4 pi epsilon naught into small r divided by capital RQ. Small r divided by capital RQ. Yes. So it will be Q divided by 4 pi epsilon naught small r by capital RQ. I hope it is clear. So clearly we came to know that this whole thing is a constant quantity. This Q by 4 pi epsilon naught RQ is a constant quantity. So we can mention E inside is proportional to small r. E inside is proportional to small r. Yes. Next come to our case number 2. Case number 2. In case number 2, outside of sphere. Outside of sphere. It is very simple and it is same as the previous one also. Outside of sphere means small r is greater than capital R. In this case, small r is greater than capital R. So let's think this is our solid non-conducting sphere. Solid non-conducting sphere, and at a distance small r, which is greater than capital R. Let's think about your Gaussian sphere. This is your Gaussian sphere. This one is our Gaussian sphere. And in this case, Gaussian sphere, in case of Gaussian sphere, this is your area dA. This is your dA vector. And in this case, electric field vector is along the direction of dA vector. So same thing we can write. Phi is equals to Q enclosed by epsilon naught. And phi is equals to how much? Phi is equals to closed integral E vector dot dA vector. Q enclosed is Q divided by epsilon naught. Because listen, within the Gaussian sphere, whole charge Q is present. Now see this thing. Within the Gaussian sphere, whole charge Q is present. Whole charge Q means the Q charge means it is available on the solid non-conducting sphere. Because within the Gaussian sphere, whole solid non-conducting sphere is placed. So now we can write this is equals to closed integral E dA cos 0. That is equals to Q by epsilon naught. Yes, and cos 0 is 1. Then it is E into integral dA is equals to Q by epsilon naught. And closed integral dA means we have discussed it is the surface area of Gaussian sphere. So this is equals to E into 4 pi r square is equal to Q by epsilon naught. So here it will be E is equals to, we can write E out is equals to Q divided by 4 pi epsilon naught into r square, or you can write KQ by r square, KQ by r square. So from this we came to know E out is proportional to 1 by r square. E in is proportional to, is directly proportional to r, and E out is proportional to 1 by r square. Then for case 3, what you have to do? At surface, on surface you have to find, on surface for case 3. At a point on surface, at a point on surface, at a point on surface, small r is equals to capital R. Small r equal to capital R means, so E on surface will be simply in the previous data, E out is Q by 4 pi epsilon naught small r square, so it will be Q by 4 pi epsilon naught into capital R square, or you may write K Q by capital R square, and it is the maximum value. You remember, surface, on surface electric field is maximum. So next part is our to draw the graph versus E versus R graph. So E versus R graph. E versus R graph. In this graph we have to only summarize the whole thing within a graph. E inside, in case of E inside, we came to know E inside is proportional to R. So let this is your small r is equal to capital R, and this is your center, and this point represents your region, represents small r less than capital R, and here small r is greater than capital R, and E surface maximum value of E. So let the point is this one. At surface the electric field is maximum. At surface the electric field is maximum, so the point will be this one. This is the point. Then E inside is directly proportional to R. So when r increases, small r increases, E value increases. The graph is linear in nature as shown in figure. Then for E outside, E is proportional to 1 by r square, inversely related. So the graph will be like this one. So this is for E in is proportional to r. Here E out is proportional to 1 by r square. And this is E max at surface. So this is about your E versus R graph in case of electric field due to non-conducting solid sphere. Then next come to our fourth application, that is electric field intensity due to thin charged infinite sheet. So our next topic, electric field intensity due to thin charged infinite sheet. Due to thin charged infinite sheet. So let us consider this is your thin charged infinite sheet. Yes, having charge present on it. These are the charges. Infinite means its dimension is very very large in comparison to our size. Yes, so and in this case the Gaussian surface will be like pillbox. We have discussed. This is the pillbox. This is that pillbox. In backside also, you may think the presence of pillbox as shown in figure. Yes, and let this area value. The area means I am going to represent. Listen. This area is A. Let the value of area of this portion is A. This is your area A. This is your area A. Yes, and the charge enclosed is Q. So we can say let sigma is equals to surface charge density. Let sigma is surface charge density. And we can write sigma is equals to Q by A, which implies Q is equals to sigma into A. Q is equals to sigma into A. Yes. So now we can find the flux. So total flux means there are three surfaces. One is your this one. Let this is your first surface. Then this is your second surface. Another one is curved surface of this pillbox type cylinder. Okay. So let flux through this surface is phi 1. Then flux from this surface, that is curved surface, the flux related is phi 2. And flux through this third surface will be phi 3. Yes. If we will draw the area vector, this is your area vector. And for this third surface, the electric field vector is along positive x-axis. For first surface also, this is the area vector. And this is your electric field vector, E vector. And for second surface, if we will consider the area vector is outward direction, this is your area vector, and electric field is along positive x-axis, E vector. Yes. So in this case we can mention total flux phi is equal to phi net. Phi net is equals to Q enclosed by epsilon naught. So phi net means flux from first surface, so flux through second surface plus flux through third surface is equal to Q enclosed is Q divided by epsilon naught. The total charge available within this portion is Q. The total charge available is Q in area A. Yes. So phi 1 value we can write phi 1 is equals to how much? E A cos 0. E A cos 0. Next, phi 2 for second surface, electric field and area vector both are at right angle to each other. So it can write E A cos 90. And for phi 3, they are in same direction. In case of third surface, that is E A cos 0. That is equals to Q divided by epsilon naught. And we can write Q is equal to sigma A. Also we can mention sigma in next line. So cos 90 is 0. So So cos 0 is 1, here cos 0 is 1, so it will be 2EA is equal to Q value is sigma A divided by epsilon naught. So after solving we will get E is equals to sigma by 2 epsilon naught. E is equal to sigma by 2 epsilon naught. In vector form you can mention, in vector form we can mention E vector is equals to sigma by 2 epsilon naught n cap. Unit vector and the direction of E vector. So this is n cap. So from this expression we came to know the value of electric field is uniform and it is independent of distance. So thus one more conclusion we can write, thus electric field is uniform and independent of distance, and it is independent of distance. Okay, so if we draw the graph between E versus R, so the graph E is independent of R, so the graph will be like this. E is constant with respect to R, and always remember this field is normal to, and we can write this field is normal to the sheet, and this field is normal to, this field is normal to the sheet. Yes, this field is normal to the sheet. Yes, so in case suppose you are instructed to find electric field due to conducting infinite sheet, due to conducting sheet, what you have to do? Electric field intensity, find electric field intensity due to conducting sheet or plate. So next come to for conducting sheet, case number 5, sorry, application number 5. Application number 5 is electric field intensity due to conducting sheet, due to conducting sheet or plate. So here what we have to write? Now see the figure first. This is your conducting sheet. One more interesting thing is available in this case actually. Listen, this is our conducting sheet and the charge given to it, this is the presence of charge. Yes, so in this case what we have to think, let sigma is equals to surface charge density, same thing, let sigma is the surface charge density and enclosed charge Q will be equal to, enclosed charge will be equal to, in this case enclosed charge Q is equals to sigma into A, sigma into A. In this case also you can think about your pillbox, Gaussian surface, pillbox type Gaussian surface, and this is your conducting sheet, means inside conductor electric field is 0, we know this thing. So what you have to draw, you have to draw the Gaussian surface like this. As per the figure you have to draw the Gaussian surface. So backside Gaussian surface नहीं होगा, remember this thing. So as electric field is 0 inside the conductor, so आउ ताकू backside आमे produce करि परिबा नहीं. Yes, so एटु मुटे hints लिखि दउची, कोन hints से लिखिबा, backside Gaussian surface नहीं होगा. As E is equal to 0. Yes. So remember one thing, जो हमरो इलेक्ट्रिक फील्ड वैल्यू चेंज हो जीवो ना, सेठी हमें गॉसियन सरफेस को स्टॉप कर दो, आ तो एक्सटेंड करिबा नहीं. सो व्हेन ई वैल्यू चेंज हो जाएगा तो गॉसियन सरफेस को वहाँ पे स्टॉप कर देना है. यस, सो हम लिख परिबा ई वैल्यू चेंज हो जाएगा तो, दिस इज फॉर कॉन्सेप्चुअल लाइन एक्चुअली, ई वैल्यू चेंज हो जाएगा तो गॉसियन सरफेस को वहाँ पे स्टॉप कर देना है. Yes, I hope this conceptual line is clear to all of you. Yes, so same thing, applying Gauss theorem in this case. Applying Gauss theorem, we will get closed integral E vector dot dA vector is equals to Q divided by epsilon naught, and it will be closed integral E dA cos 0, that is Q by epsilon naught. Cos 0 is 1, so take it outside E, then closed integral dA, closed integral dA, that is equals to Q divided by epsilon naught, and here closed integral dA will be, this value is A, area A, this value area A, so E into A is equals to Q by epsilon naught, and Q is equal to sigma A, Q is equal to sigma A by epsilon naught. So after solving you will get E is equals to sigma by epsilon naught. Yes, in vector form, you remember in vector form E vector will be equals to sigma by epsilon naught into n cap. This is in case of vector form. So this is your E conducting, and in previous case we have discussed E for non-conducting. So E conducting sheet 1 conclusion, you may write this conclusion, this may come in your board exam. Conclusion is E conducting is equals to sigma by epsilon naught, and E non-conducting is equals to sigma by 2 epsilon naught. It can be written 1 by 2 into sigma by epsilon naught, and instead of sigma by epsilon naught, instead of this sigma by epsilon naught, we can write 1 by 2 into E conducting, 1 by 2 into E conducting. Yes, so the conclusion is E conducting is equal to 2 times of E non-conducting. So E conducting is equals to 2 times of E non-conducting. Electric field due to conducting sheet is equals to 2 times of electric field due to non-conducting sheet. This is our aim. Yes, I hope it is clear to all of you. So let's solve one numerical after this application number 5. I hope up to 5th application it is clear to all of you. Let's solve one numerical. So question is, find electric field, find E at A, E at B and E at C from the following figure. So the figure given is this one. This is the figure given, and in first plate the surface density is sigma, for second plate the surface density is minus 2 sigma. Yes, the point given, this is point A, this point is B and this point is C. I hope this question is clear to all of you. Yes, next, now starts to solve the question. Answer. So first thing, we have to draw the diagram first. The point at which we are going to calculate the electric field intensity, first we have to place a Q naught charge in order to find the direction. So let us place a Q naught amount of test charge. Yes, so this is suppose your first plate, this is your second plate, name like this. Then it is sigma, first plate ro charge density kete sigma, that means this is positively charged plate. A positively charged plate Q naught को कौन करेगा, हमारा रिपेल करेगा, Q naught को से रिपेल कला. So this is E1 vector, and this is second plate is negatively charged plate, this will attract Q naught. So this is your E2 vector. So हमें easily से अनुसार नेमिंग देगा E1 vector and E2 vector. Okay, so E1 vector value केते होबो, E1 vector will be sigma by 2 epsilon naught. So it will be sigma by 2 epsilon naught, and the direction is minus I cap. The direction is minus I cap along negative x-axis. And E2 value, E2 vector will be surface density is minus 2 sigma. You have to consider the magnitude, because in first chapter जते सब हमर concept electric field concept कोड जे रहला Coulomb force रो electric field intensity force per unit positive charge. in coulomb force we have to take the magnitude of charge. That means electric field में magnitude सब नवा. So magnitude नेला मैंने हमारा आंसर आसला 2 sigma by surface density divided by 2 epsilon naught. So it will be sigma by epsilon naught, and the direction is I cap plus I cap. I hope it is clear. Yes. So now see one thing, E2 and E1. So net intensity केते हम पाइबा? Net intensity will be E net. E net vector is E1 vector plus E2 vector. E1 vector plus E2 vector. So it will be E net. E net is equal to E1 vector is sigma by 2 epsilon naught minus I cap plus sigma by epsilon naught plus I cap. Yes. तो आम इजिली आम कैलकुलेट कर बर्तमान. सो दिस विल बी आम जब नवा के आई कैप कमन नहीं गले तो सिग्मा बाय इप्सिलॉन नॉट कमन नेले सिग्मा बाय इप्सिलॉन नॉट आई कैप जब आम कमन नेले रहा के 1 माइनस 1/2 1 माइनस 1/2. दैट मीन्स 1 माइनस 1/2 इज प्लस 1/2. सो इट विल बी सिग्मा बाय 2 इप्सिलॉन नॉट आई कैप एंड दिस इज द ई नेट एट ए. This is the value of E net at A. I hope this question is clear to all of you. Yes. Next come to your second part. In second part, what you have to do? See the diagram properly. At B. Next we have to solve for at B. At B आम कौन करिया गोटे Q नॉट प्लेस कर देली. Q नॉट प्लेस कला माने फर्स्ट प्लेट, दिस इज योर फर्स्ट प्लेट एंड दिस वन इज सेकंड प्लेट. बर्तमान देखो क्वेश्चन. फर्स्ट प्लेट कौन करिवो? फर्स्ट प्लेट पॉजिटिवली चार्ज प्लेट. Q नॉट को से रिपेल कर देला. Q नॉट पॉजिटिव टेस्ट चार्ज. सो दिस इज योर E1 वेक्टर. सेकंड प्लेट नेगेटिव चार्ज प्लेट से Q नॉट को अट्रैक्ट कला. सो दिस विल बी E2 वेक्टर. सो E1 and E2 both are in same direction. Yes, at B. So what is the value of E1 vector? E1 vector is equal to sigma by 2 epsilon naught I cap and E2 vector is equals to E2 vector 2 sigma by 2 epsilon naught I cap, that is sigma by epsilon naught I cap. Yes. Okay. So E net is equals to E net vector is equals to E1 vector plus E2 vector. So E1 vector value, that is sigma by 2 epsilon naught I cap plus sigma by epsilon naught I cap. So after solving you will get, it will be 3/2 sigma by epsilon naught I cap. This is E at B. Net electric field intensity at B. This is the answer. Then at C. At point C. At point C again, to find the electric field intensity, you have to place a Q naught charge. A Q naught charge, वो unit positive test charge गोटे. A Q naught गोटे test charge. बर्तमान first plate, this is your first plate, and this is your second plate. First plate positive charge plate, Q naught को repel कला. Yes, so this is E1 vector. Second plate is negative charge plate, Q naught को attract करिवो. So this is E2 vector. So now again you write E1 vector value sigma by 2 epsilon naught I cap and E2 vector value 2 sigma by 2 epsilon naught into minus I cap. So it will be sigma by epsilon naught into minus I cap. So E net vector at C, that is E1 vector plus E2 vector. So E1 vector plus E2 vector means sigma by 2 epsilon naught I cap plus sigma by epsilon naught minus I cap. So common केते गला sigma by epsilon naught I cap common गला. एट रहा आमर 1/2 minus 1, that is minus 1/2, that is minus 1/2. Yes. So this will be minus sigma by epsilon naught, sigma by 2 epsilon naught I cap. Yes. So this is E at C, E net at C. A minus I cap direction means it is towards leftward. Net electric field at C or leftward. Clear. And plus I cap कोठी बाहर लामरो, plus I cap बाहर लामरो both case रे at A and at B rightward होची. Net electric field is at rightward. I hope this type of question is clear to all of you. এই type of question को एमती ही solve करे आजो. Okay, with direction and magnitude you can write in a very precise manner. Yes. Okay. Again देखिए आउ गोटे क्वेश्चन सॉल्व करिया. एई टाइप रो आउ गोटे क्वेश्चन सॉल्व करो. देखो नेक्स्ट क्वेश्चन जिबा Come to the next question. Same question. Find E at A, find E at A, E at B and E at C. So figure कौन देला given? Figure is like this. This is the figure given. So this is your first plate, this is your second plate, and your charge density sigma. Here it is minus sigma. This point is A, this point is B, and here this point is C. Same thing. Okay. ଆମେ ଯିବା ବର୍ତ୍ତମାନ at A କରିବା. At A first solve the case. Answer at A. So जोटी ଆମେ solve କରିବା सेठी कोन करिवारे at A we have to think a Q naught charge. Q naught. So first plate is positive plate, second is negative. So now tell ବର୍ତ୍ତମାନ in case of first plate, at A first plate positive charge plate, so Q naught को repel कर देला. So this is your E1 vector. And second is negative, so it will attract Q naught. So this is E2 vector. Simply we have to write E1 value and E2 vector value. So what is the value of E1 vector? E1 vector is equal to sigma by 2 epsilon naught minus I cap, and E2 vector is equals to sigma by magnitude nova sigma by 2 epsilon naught into plus I cap. Yes. Okay. So what is E net? E net is equals to E1, E net vector is equal to E1 vector plus E2 vector. So it will be sigma by 2 epsilon naught into minus I cap plus sigma by 2 epsilon naught into plus I cap. The value will be 0. So this is E net at A. So this is E at A. Finished? Yes. Next come to your at B. At B, find the net intensity. So in case of at B, B point में Q naught charge place कले, Q naught charge place कला परे first plate positive charge plate, so Q naught को कौन करिवो repel करिवो. Yes, E1 vector. Second plate negative charge plate, so it will attract Q naught, E2 vector. So again you write E1 vector is equals to sigma by 2 epsilon naught I cap, and E2 vector is equals to also sigma by 2 epsilon naught, that is also I cap. Yes. So what is E net at B? E net vector at B is equals to E1 vector plus E2 vector, that is sigma by 2 epsilon naught I cap plus sigma by 2 epsilon naught I cap. So it will be 2 sigma by 2 epsilon naught I cap, that is sigma by epsilon naught into I cap. This is the answer. Plus I cap means towards rightward. Sigma by epsilon naught I cap. This is your E net at B. Then come to the solution for at C. At C. Okay. At C. Okay. At C, place a Q naught charge. So positive plate, first plate तब कौन करिवो Q naught को repel कर देला. So this is your E1 vector. Second plate will attract the Q naught. This is E2 vector. So in this case, what is the value of E1 vector? E1 vector is equal to sigma by 2 epsilon naught plus I cap, and E2 vector is equal to sigma by 2 epsilon naught into minus I cap. So E net vector at C, that is E1 vector plus E2 vector. So it will be sigma by 2 epsilon naught plus I cap plus sigma by 2 epsilon naught into minus I cap. So it will be 0. This is the answer. Yes. So जो type of surface charge density given थी वो question रे, according to that you have to put the respective value. Yes. I hope up to this it is clear to all of you. So हमारे lecture रे हमें कौन सीखिले? These are the applications of Gauss theorem. अब केमते हमें बर्तन relation find कले E non conducting and E conducting relation, that is actually truly important. Yes. So go through that concept properly and write each and every concept in your copy in a very systematic manner. Yes, I hope this lecture is clear to all of you. So thank you. Have a nice day and kindly like, share and subscribe this channel. Okay.